Welcome to Networks Professionals.
Imagine for a second a world where the internet just ran out of space. Literally. No new devices could connect, no new network sessions could be built. Sounds crazy, right? But that was a very real, looming disaster a number of years ago with the IPv4 address shortage. We were entirely running out of unique public IP addresses to hand out to this massive explosion of connected devices. But, spoiler alert, we managed to save the modern internet, and we did it with a rather ingenious piece of network engineering. Welcome to today's Explainer. I am so incredibly pumped to guide you through this, because today we're unpacking exactly how that rescue operation actually works and how it's secretly keeping our networks functioning every single day. Let's dive in. Look around your own home or office right now. I bet you've got a laptop, a smartphone, a smart TV, maybe a tablet or two, all connected to the Wi-Fi. It's a lot of devices, yet your internet service provider is only giving you a single public IP address. So I want you to really think about this critical question. How do hundreds of devices share one IP? Well, that right there is the core problem that our subject today solves, and it solves it on almost every single network across the globe. To wrap our heads around this clever little solution, we're going to break this explainer down into 4 quick parts. First, we'll meet Pat. Second, we'll look at how Pat translates traffic. Third, we'll cover the big benefits. And fourth, we'll talk about when Pat falls short.
Okay, Section 1. Meet Pat, also known as NAT overload.
Meet the absolute protagonist of our explainer, Port Address Translation, or PAT. Now, PAT is basically an extension of Network Address Translation, NAT, and its whole job, its entire purpose, is to allow multiple devices on a private network to share a single public IP address. But the absolute magic of this process? That happens right here, in how it works. It pulls off this many-to-one translation by assigning unique Layer 4 port numbers to each and every outgoing connection. Honestly, this is exactly why it's so accurately nicknamed NAT overload in the IT world. It is literally overloading a single public IP with multiple connections just by utilizing those unique ports.
Moving right along to Section 2, Traffic Translation, how PAT actually works.
To really get the mechanics here, we need to picture the specific journey of a single data packet trying to brave the public internet. When a device on your internal local area network initiates some web traffic, PAT immediately steps in to modify the packet header. Let's walk through it. Step 1. The packet leaves the device with its internal private IP address, let's say 192.168.1.10, and an original source port, something like TCP 1500. Step 2. This is where the router acts like a diligent bouncer at a club. It stops the packet, takes away its private ID badge, and swaps it for a temporary public one. The router literally replaces that internal IP with its own single public IP address and replaces that original source port with a unique, dynamically assigned port number from its own available pool. Finally, Step 3, and this is crucial, the router logs this entire swap in a translation table, so it doesn't forget who is who.
Think of it like a meticulous, highly organized ledger. We call this the router's dynamic translation table. You've got the internal network identity, that 192.168.1.10 with TCP 1500, mapped directly to the public face, which is the router's IP and the dynamic port. Why is this ledger such a big deal? Because when the external server out there in the internet finally responds, it sends the traffic back to the router's public IP and that specific translated port. The router just checks this very table, maps the port right back to the original internal IP and port, and safely forwards the data back to the correct internal device. It is seamless.
All right, Section 3. The big benefits. Why do we care so much about this operational efficiency?
Just consider the absolute power of the number 1. This single digit represents the ultimate cost efficiency and IP conservation of PAT. Because of this exact technology, hundreds of internal devices need only one purchased public IP from an ISP to operate globally. It literally solved the IPv4 address shortage by just massively compressing our need for public IPs. You don't have to buy a public IP for every single phone, tablet, and computer in your building. You just need one. The whole shebang runs on one IP. And that leads to a really brilliant, vital secondary benefit: security through obscurity. Because your router is stripping away the private internal IP address and replacing it with its own public IP, your internal addresses are totally masked from external networks. The router acts as this incredibly effective shield against the outside world. It makes it extremely difficult for malicious actors to directly target your internal devices because, well, they only ever see the router. They never see the vulnerable device hiding safely behind it.
Which brings us to Section 4. It's not all sunshine and rainbows. We need to talk about when PAT falls short and its strict mathematical limits.
As incredibly effective as PAT is, it isn't magic, right? It's bound by math. Think about this specific number, 65,535. In the networking world, resources are strictly finite, and this number right here represents the absolute maximum limit of TCP and UDP ports available, period. So that brings us to a huge pain point called port exhaustion. Remember that dynamic pool of unique ports the router uses to label outgoing traffic? Well, those TCP and UDP port numbers only range from 0 to 65,535. And actually, scratch that, the available pool is even smaller because the first 1,024 of those are strictly reserved for well-known services. So PAT has a hard mathematical ceiling. If a network is incredibly busy and all of those available ports get used up, you're looking at a catastrophic network failure. Additional internal devices will be entirely blocked from making external connections. If the router doesn't have a free port to assign you, there's no way around it. You simply don't get on the internet.
And beyond just running out of ports entirely, PAT also struggles depending on the type of traffic you're sending. Basic, simple protocols, they adapt to these dynamic port changes on the fly with zero issues. However, complex protocols, stuff like VoIP phone systems using SIP or active FTP transfers, they do not dynamically adjust to port translation well at all. In fact, they can totally break during the translation process. For those complex protocols to survive, they often require application layer gateways, or ALGs, or highly specific custom configurations just to navigate the router's translation tables successfully. It's definitely an added layer of headache for network administrators.
Which leads us directly to the practical application of everything we've talked about. Understanding these mechanics, the bouncer at the door, the meticulous translation ledger, and those hard mathematical limits gives you incredible power over your network. So I'll leave you with this final provocative thought. Would you like to know how to configure PAT on a Cisco router? Or are you maybe trying to troubleshoot an active port exhaustion issue right now? Whatever it is, the knowledge we've covered today is the exact foundation you need to tackle either challenge. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.
Thanks for watching.